So my name is Adam Granitz, or Granitz Adam. That's an irony. And I represent my own company. It's called IntelliFactory, and I also work for EPAM Systems. And today I'll be talking about making programming functional. This is a bit of a misleading title. Actually, what I would like to talk about is an introduction, a short introduction to this language called F#. Now you may have guessed that it's a language for the .NET framework. So this is one of the newer additions to the framework, and actually it is a functional language. How many of you have ever heard about F#? Okay, that's good to know. In what context? Have you guys worked with F# before? Just seen it. Okay. So because I wasn't sure how many people will have seen F#, I actually prepared half of the presentation roughly about medium to semi-advanced topics in functional programming, and in particular F#. So let's get started. So this is what I'm going to be talking about today. I'll give a short motivation for functional programming, why this new paradigm, actually it's not a new paradigm, it's been around for more than 50 years, but it's a new paradigm for the commercial world. Many of the companies that are doing commercial development are just discovering functional programming the first time. So I'm just going to talk about a little motivation for that, and also go into more depth about the functional programming concepts that drive all the advantages behind functional programming. And then we look at F#. We check out its syntax, a few constructs. In particular, there are 4 sets, if you want to categorize these constructs, that we can talk about in relationship to F#. There's functional, object-oriented, imperative, and language-oriented constructs. And I'm not going to be talking about the object-oriented and the imperative features because it doesn't make sense. We'll briefly look at them if somebody wants to see them, but I would put the emphasis on the functional and language-oriented constructs. And then at the latter half of the talk, we are going to take a look at the environment in Visual Studio and how you can embrace this new language and use it real quickly. And then we are going to look at something called the F# Interactive. This is a top loop environment in which you can type stuff and you get immediate feedback, which is very useful to develop some stuff on the fly. Okay, so the motivation. So what do we have today? Well, I mean, anybody who has done serious software development knows that people make mistakes, and especially programmers. So we had probably all seen all kinds of weird code. So the human imagination is just unbelievably wide. Even if I asked all of you here just to write a simple algorithm, we would probably get as many different approaches as we have the number of people here. And that is a staggering fact if you consider that the state of development, software development nowadays, is trying to converge into a predictable and controllable process. So that is actually a huge issue here, that people make mistakes and we all think in a different way. So what would we need to sort of bypass this or bridge over this difficulty or problem? Well, we need more effective abstractions so that we can express what we need using fewer lines of code. Imagine that, you know, we take a system that was developed in C++, let's say 20,000 lines, and somebody came up here and said, all right, we can do this in 100 lines. What would you think? I think that would be pretty cool. So one way to actually accomplish that is to change the language, introduce a different set of abstractions that people can use in the language to then be able to get accomplished more. And then one of the pillars of that is a better type system. If we go back and think about what we did in the 80s and 90s when we programmed in C, you may recall we had some things called pointers and references and all kinds of other dangerous mechanisms that allowed us to cast away values into other types, access the underlying memory representation by bits, and all kinds of very dangerous things. These should not be allowed in now in today's computing or software development processes. So if we had better abstractions and a better type system, we would have fewer, actually almost no conceptual errors. This would be quite nice. And of course, having fewer lines of code would mean fewer bugs and defects, and in the long run, better maintainability. So this sort of relates to all the business aspects. I'm sure most of us here are techies. So I'm going to go on and look at a more distant motivation. What we actually really wish for are two things. We should be able to synthesize programs, and we should also be able to check the correctness of a program. So if all of us here implemented something, and if I had a tool that we could put these programs into, and the tool would say yes or no, depending on whether the program was implemented correctly or not, that would be a huge advantage. We could immediately filter out everybody else who is not doing a good job in programming, and just leave those who are. So program synthesis is actually something that is it has a fairly significant research background for many decades now. So basically this means that we want to generate programs and in fact take away humans altogether and generate programs by a tool. We had seen many examples nowadays. If you use the Java language, for example, there are a couple of great programming environments, such as Eclipse and so on. Most of these tools generate, even if you don't know it, they do generate thousands of lines of code in a larger size project. So already we are synthesizing lots of lines of code. We just don't know about them most of the time. Or if we do, we don't appreciate the fact that a computer program is writing programs for us. So here what we would like is actually have some sort of a formal specification by which this generator program could synthesize programs for us. And so this is actually a shift towards a more declarative style of programming in which we are not concerned about how to get something done, but instead we are concerned about what to get done. If you think back maybe in your college or university years, you may have done some logic programming. So logic languages is a paradigm actually, which is almost entirely declarative in nature. So you tell the facts and you tell the clauses that can derive new knowledge, and then you ask questions. You're not concerned about how the question or the answer to the question is derived. All you care about is to get the answer. All right, so of course, as we said, this would eliminate most of the errors or all of the human errors. And this would be really great to have some more comprehensive tool suite that could synthesize programs for us. Checking the correctness is seemingly a distant plan. I'm sure most of you have thought about this. And again, as with program synthesis, formal verification, proof or theorem provers, and other formal environments had been around for 2 or 3 decades. So this also has a significant amount of research background. Here basically we want to verify that a program fulfills a specification, for example, the same specification that we used that possibly to generate these programs automatically. And what we can use is, for example, we can take a theorem prover, we can formalize our descriptive language, the specification language, and then let the theorem prover do the job and sort of try to analyze what we came up with. And we also have model checkers and all kinds of formal, sometimes difficult to use, sometimes easy to use environments. Just one example from the top of my head for model checkers. For example, in Intel, where they design chips, or any other chip designing companies, they are involved heavily in the area of formally verifying that the circuits that had been designed actually are correct. So, and we will, well, I hadn't prepared any slides on that, but I can, after the talk, give you some pointers to some work in functional programming languages, and you could see how easy it is to implement something like that. Just in a few lines, you can already be doing model checking for a subset of the problems that are involved with new chips. All right, so this is basically the distant and semi-distant motivation for something that we would like, but I don't think that we still, or maybe we don't already have the idea of how this relates to functional programming. I think by the end of the talk, that will be clear. One pointer that I can give now is functional programming is drastically different from, for example, object-oriented programming or imperative programming in the sense, and we will be talking about that shortly, but one thing that is actually very, very easy to remember is that pure functional programming languages don't have mutation. So if you take that aside and sort of just concentrate on that one single fact, you can see how that sort of relates to checking, for example, program correctness. It's much easier to do that if you don't have side effects. You don't have to trace weird accesses to memory locations from different places. Everything is straightforward. You know if a value exists, it will never be changed. So that sort of gets you the idea how we can actually accomplish some of these better with functional languages than with other languages. And I'll just leave it with that and continue on. So let's talk about some functional concepts. What are the main pillars of functional programming? When can we say that a programming language is functional? I mean, this is a pretty central question here. Well, probably in the number one pillar of functional concepts is the higher order functions, the existence of higher order functions, or HOFs. So what are higher order functions? Well, these are nothing spectacular, really. I mean, they sound awfully difficult to grasp. But these are really just nothing more than functions that take other functions. This is the easy part. We had seen already in other languages that you can pass a pointer to a function in C, or I don't know, classes that implement different methods that can be called via the receiving object and so on. So all these other paradigms, be that imperative or object-oriented, have some way of sort of mimicking higher order functions, or at least the aspect of passing functions. What they can't, or difficultly can simulate, is actually passing back functions. In other words, calculating functions. So the return value can also be a function. And so that's the full definition of a higher order function, something that takes either function parameters and or return functions as a result. And I'm not talking about returning a reference to a locally defined function. I'm talking about actually computing a function. So depending on the parameters, getting back a different function. And that's quite a conceptual leap compared to what people can imagine in Java, for example. So obviously this gives a rise of first-class values for functions. They basically get the same status as integers or strings or any other values. They become first class because they can be passed around. First class values, functions as first class values, and higher order functions are essentially the same thing, but one is coming from a language oriented terminology, if you will. The other one is more of a theoretical definition. And we also have anonymous functions. These are just nothing spectacular. These are functions that don't have names. You can just easily define a function, specify the parameters, and say what the function does, and you can pass it back. And we had been starting to see these anonymous functions. Sometimes people call it closures, which is incorrect, or lambda expressions in C#, for example. These are the same thing. Okay, so that's HOFs. The other main pillar of functional programming languages is immutability. This is what I was talking about earlier. Basically, by default, a purely functional language has no whatsoever means to mutate an existing value. You can create values, and that's it. You can pass the same values, but you can never change it. So you may ask, okay, so how do I accomplish mutation then? How can I have, for example, a tree structure and put elements into it? Well, it's very easy. You take the tree structure, and when you add the new element to it, you create another tree structure with exactly the same structure that existed before, plus the additional element. So you would think, okay, so why the heck would I do that and create new values every time I mutate a structure? Wouldn't that slow me down? And the answer is actually no. Because, and this is where the magic comes in, the compiler is able to take care of all the details behind making that efficient. So although we don't have to be concerned about mutation, actually the compiler is translating all this logic into mutation, probably. But we shouldn't be concerned about that. The third pillar is currying. I don't want to have a computer science lecture here, so I'm not going to go into what currying means. It just simply means that you can have a function that expects more arguments, but you don't give it all of them. So when you apply that function, let's say we have a function that takes 5 parameters, but we apply it only to 4, then we get back a function that takes the additional 1 more parameter, and then that function will compute the value. So this sort of relates to closures. Closures are basically, you can say that they are anonymous functions that have a context around them. And basically with currying, in the example that I just mentioned, the 4 parameters pushed at the first invocation would be in the context of the closure. And enough of that. All right. The fourth pillar is actually polymorphism. If you think back to the C++ years, that's when polymorphism sort of first appeared in the mainstream languages, at least. We had something called ad hoc polymorphism. Ad hoc polymorphism means that you do a textual replacement of the type that is instantiated into a generic type. So for example, you had a set implementation, something that just implements a set data structure, and you instantiated with an int or integer type. What happened is the compiler took all the textual, all the source code for your set class or whatever, and plugged the int type into it and compiled it, and basically generated some code which was special for the integer sets. If you did the same thing with strings, it would generate another piece of code that could only handle string sets, and so on and so on. It's called ad hoc because that's not what true polymorphism is about. True polymorphism, or as it's in the literature called parametric polymorphism, means that you will generate the same code no matter what type you are instantiating. And how can you do that? Well, basically everything is a reference. Everything is boxed, so to say. So the code that is working on objects doesn't have to care about what's inside or what's referenced from these boxed objects. It doesn't care. So that's what parametric polymorphism is. And F# and most of the other functional languages support that. So the type system is much more rich. We have type variables. We have basically what is called the algebraic data types, which can involve multiple type holes, things that we don't want to specify at the time of specification. So basically they remain polymorphic and can be instantiated at any later time, either bound completely or remaining truly polymorphic. So for example, here's a map object. Just like in C, I use the C# syntax here. This map actually takes 2 type variables, T1 and T2, and you can imagine what it does. It's a map of keys of type T1 being mapped to objects of type T2. Okay? The other central concept in functional programming languages is the type inference. Type inference basically means the automatic discovering of types. So you never have to annotate, well, never is a bit of a stretch. You don't have to usually annotate your programs with types. You can just say f of x plus y, or f of x and y equals x plus y. You don't have to say what the type of x and y are, because it will be inferred. It will be found out later. So basically this means that there's a type inference algorithm, which is run on the middle phase of compilation. This is part of the semantic analysis phase, and you try to discover what the different values, what type they can be. And if you find a mismatch, For example, somebody thinks that this type here or this value has type A, but then later on that type turns out to be B, and A and B are not compatible, then you will get a type error. So it will not say at the first instance, hey, it shouldn't be A, it should be something else. It will only say when there is another occurrence of that using of that value with a different meaning or a different type. Then we get a semantic error. So we don't get type errors, although they surface as type errors, but actually what they are semantic errors. So these are holes in your logic. So if a programmer wrote bad code, it would be almost automatically realized, and the compiler would point out the place of error. All right, we have a couple more things. Something called the lazy versus eager evaluation. Some of you may have heard about the difference between the two. Lazy evaluation means that we only evaluate something when it's actually needed. And eager means the opposite. Eager means we evaluate it immediately as we see the value. So if I had a program that consisted of 2 lines, and the first line would be a function call that binds the return value to a variable, and the second one would be a line that does not use that return value, and the first line would result in an infinite loop, you would still have your program running. Because there's no need whatsoever to execute the first line if it's not needed for the second. Whereas in an eager evaluation language, you would just run into the infinite loop and loop forever. Okay, and the last piece, I think, is recursion. I mean, functional languages sort of lend themselves very naturally to recursion. This applies on several areas. It applies to values, applies to types, and of course to functions as well. So typically if you look at a functional programming language and you see the kind of code that is being written, you will see that many of the functions that attack some big problem want to do it by recursively trying to solve smaller problems. In other words, breaking down the large problem into a small one and recurse on that small problem and try to solve that. So basically there's always a base case and there is a case which results in recursion, which from theoretical computer science we had seen that kind of stuff. On the level of data, this means that we can define data structures or pieces of data or values that are referencing some parts of their own piece or data. In other words, these are referentially, or what is the right word for it, recursively defined. So I may have a list, a data structure, or an infinite sequence of numbers, basically referencing itself. And I will have some examples of that later, so we'll see how they look like. And with types, this is fairly straightforward. We have a type, or we have more than one types that are mutually recursive with respect to each other. We'll see maybe some examples for that. Okay, so finally, we had discussed why functional programming is sort of good. I think most of you have the idea. And we discussed some of the main pillars of functional programming. And so now let's look at a language. Let's look at F#, which is a functional and object-oriented language. So basically, the reason why it has object-oriented support is manifold. I will only mention one, but very convincing argument. It's on the .NET framework, and everything on the .NET framework uses objects and classes. So the only way to be interoperable is to be actually compliant with object-oriented paradigm. And so imagine a language that looks like C#, but actually is much more clean. We'll see some code segments soon. And has some functional ideas. But unlike C#, we are not trying to incorporate functional paradigm or functional ideas into a non-functional language. We are doing it the other way. We start with a clean and nicely defined core functional language and putting objects onto it. And the overall result is just staggering, and we will see that later. So basically, this functional object-oriented language is strongly typed, so it's type-safe. It supports a type inference engine, and it's garbage collected. It's pretty mainstream nowadays. The code itself is very succinct, expressive, and composable. Naturally, one of the cornerstones of functional versus object-oriented languages is actually how easily you can compose something. And with functional programming languages, because the main abstraction mechanism is a function, you need to be able to compose the functions. So everything is basically heavily backed up by some mathematics behind. And so composability comes from that. Expressiveness and succinctness, we'll look at that later, and you can decide yourself. We talked about interoperability with the .NET languages. Basically, F# is also compiled to the same instructions as any other .NET language. And because of that, they can, or you can access the same libraries that were written in other .NET languages in F#. And you can do vice versa. So from C# you can access F#. And you also have access to full .NET runtime support, all the tools, all the libraries, all the third-party stuff, anything. You can read more about these different dimensions and the different arguments for F# on this website here. As you may know, F# started out from Microsoft Research, and now it's making its way into the Visual Studio suite. So it will be part of the next version of Visual Studio. And with that, it actually went and was transferred into the development division of the company. So although the key people behind F# are still doing Microsoft Research work, it's actually being picked up by the development division, which means a rapid acclimatization, and basically spreading the word in mass dimensions. And this is a point where I'm supposed to give you some F# code samples. I think, let's do that. So most of these will be examples later on, so I'm not going to just go into it. As you can see, we have this funny keyword that says let, which you may have seen in some obscure languages. And you may wonder, why the heck do we need a keyword to introduce a value in a language which doesn't support mutation? So this is called a binding. When you say something let, something equals whatever, that's a binding. That means that value is being bound or labeled using that name. It does not mean that you can change that name or the content of that name. So this is not the same as a variable. This is why it's called a binding. Well, you can, and this is why I said in the beginning, I don't want to talk about the imperative features. You can designate or put an additional attribute on this binding to designate that it's mutable. But we don't want to show you some bad stuff. So let me just switch back and go on. So there are 4 different areas of F# constructs: functional, imperative, object-oriented, and language-oriented. Language-oriented is this funny thing that we coined. This is a term that hasn't existed in this context before. Language-oriented means that we are concerned about various different internal representations and transformations that take values in one representation to the other. So this is a very abstractly defined notion. And there are a few examples and mechanisms that will be mentioned later on for language-oriented programming. One of them is active patterns, reflection, and quotations, and then different abstract syntax tree representations. I'll talk about those later. So we're not going to cover 2 and 3, but we will cover number 1, basically functional constructs, or some of them. We'll look at some concise syntax or the examples of how the syntax actually matters. And then we look at, in particular, a part of the abstraction layer that deals with data or values. We look at the mechanisms or the different data abstractions that you may not have seen in other languages, but are believed to be, you know, the vehicle for fast and expressive programming or program development. And some of those include discriminated unions. These are also called labeled unions, pattern matching, polymorphic abstract data structures, and type augmentation. We'll see what those are in a minute. And then we'll also talk about control abstractions, which is actually, I think, one of the biggest area with respect to F# as a language. Control abstractions, and in particular computation expressions, at the moment can assume 3 or 4 different forms. I'll talk about each of those briefly. Okay, so I don't want to spend too much time on the syntax because anybody who sees the code is pretty much able to pick it up fast. There is one slight or subtle issue that people should be aware of, and that's the traditional versus the light, so-called light syntax. You can put that hash mark light in front of your file, and after that the compiler assumes that it's written in a light style, which means fewer keywords, more compact code, but also the tabbing and spacing. Actually, you can't use tabs, you can only use spaces, but indentation does matter. I don't know if you probably worked with make files before. Same thing there. If you don't put the right amount of indentation, it will complain. So on the left side, you see an ordinary function in the traditional style. It's a function that takes 2 parameters, a and b, and does some magic with them. For example, it adds them and subtracts them, and assigns or binds those 2 values to c and d respectively, and then returns their product. But as you see, I mean, this is pretty hard to read because they are not indented. I don't see any scoping information readily. So on the other side, on the right side, actually you can see the light syntax form, the same function f with a and b parameters, the same c and d local variables or bindings defined for the sum and the difference for those a and b parameters, and then the multiplication of c and d. But the body of the function is indented, and the compiler will actually complain if you don't indent it. So this is sort of one step towards automatic code formatting, and also one step for maybe program synthesis later on. We want to free, for example, companies that employ developers, F# developers, from having to worry about people's styles. There is a set style, it's called the light syntax, and everybody has to use it. It has some pretty rigid guidelines, what you can or you can't do. And if you conform to it, then most of your code will be pretty standard and comparable to other people's code. So that's one of the advantages of light syntax, and we solely prefer the light syntax over the traditional one. Piping functions is something to put functions together and pipe them. Here you can see an operator, a pipe operator defined, which takes two things. It's actually an infix operator, so it's you would see this as x and then the operator and then a function. And what it does, it basically applies the first argument to that operator to the second. So this is like piping, pushing values through. This is pretty standard functional core concept. The other one is similar. It's function composition, taking 2 functions and a value, apply the value on the first function and pipe the result into the second function. Pretty standard stuff. But using these extra operators, basically you have a more functional style programs, and also type inference in many cases is helped with this reformation of your code because you're pushing type information from the left to the right, because the final argument to any of the functions is said or mentioned first, as we will see in a second, in a few slides from now. I'll refer to that back. Okay, one of the main data abstraction is a discriminated union or labeled union. This basically means I'm defining a type that has more shapes. Exactly, in this case, 5 different shapes. So an expression can be a number, or it can be an add or subtract or multiply or divide term and nothing else. Not like in Java, for example, you may define the same classes that implement different logic that relate to these different primitives, but there you don't get the completeness. You may pass another function which happens to implement the same thing, yet the compiler will not complain. Here, if you have a value that is claimed to be of type exp, it can only assume one of those 5 forms and nothing else. But note how I recursively define this type. So a subtract term, for example, can have 2 subterms that in turn are again of type exp. So basically I can represent just about any algebraic expression using that discriminated union type. And if I wanted to write an evaluator for that type, I could just type up a recursive function that says, all right, let's take a value of type exp. If it's a number, then it carries an integer value on it, and that will be the result value of this eval function. If it's an add term, then it has two subterms. Well, we want to recursively evaluate both and then add them. And the same for subtract, multiply, and divide. And that's all. Using these 6 lines, I have an interpreter for this representation. So now it's time to sort of switch into this. It's terrible. F# interactive. This is a Visual Studio plugin, which is on the right side, that small window there that says F# interactive on the top. What I can do is I can go in my F# code, I can highlight anything and then press Alt-Enter. And what it does, it pulls it over into the interactive window and sort of puts it in like if I typed it in there. So this top loop then answers me and says, all right, I've noted that you defined the type exp, and this is what I can do. So now I could say something like, okay, number 1. Well, it says, okay, I understand it. Val means value. It is just a name for the last entered expression. And it has a type of exp. See, it already discovered that it has type exp, and the value of it is just number 1. Okay, then I could say, all right, let's pick up my evaluator. Okay, it says fine. I have a function called eval, and it takes an expression, and it will return an int. So if I had been smart enough to store a binding to that number 1, let's say I put value 1, and just basically do that, define another value. I mean, this is pretty silly, but it just shows you that I have a different representation, and I can use the constructors to create values in that representation, and I can compose them very easily. I could say, okay, add those 2 things. If I could find, just basically add v1 and v2. So now I have an e, a binding for e, which is an expression that is 1 plus 2. Then I can say, well, let's evaluate e. And indeed, it's 3. All right. So let's switch back here. So we tested that. Okay, another abstraction is basically how polymorphic abstract data structures can be defined. We talked about that, type variables. Here we have a list, an array, a sequence, a map, a set, and so on. These are all built-in types. They can be instantiated with any type. If I wanted to create my own, for example, there is a tree type. Note I put a type variable in front of it. It says any type, and I will call that A. And a tree type can do, or can assume 2 different shapes, either a node shape or a leaf. If I have a node, well, this is a binary tree. So I will have a value of type A carried on that node. And I will also have 2 subtrees, which basically are the left and the right subtrees. So this is an easy definition, a recursive definition of a binary tree that carries any value. So if I instantiated this and say, all right, I have a node that contains the number 1 and 2 leaf nodes, that would be an int tree. We could do that, but I think I'm running out of time soon. So, okay, besides discriminated unions and recursively and polymorphically definable data types, we have something called tuples. These are basically just nothing more than pairing values together. Recall that in most traditional languages, we always had difficulty returning more than 1 value. If I had a function, for example, give me my name, and I gave my birthday, and it would return my name, that's just 1 value. It returned my name. But what if I want to return a name and my age? Well, I have to wrap it into an object. So I have to define a class. I have to create a new instance of that class. I have to fill the fields. And then I have to return that object. And so it's a pain. So what F# does is basically you can put parentheses. And well, you don't need the parentheses, actually. All you need is a comma. You can start pairing values together. The first example, I paired 2 things, 1 and 2 together. In the second, I paired 2 tuples together. In the third, I have a a list of ints 1, 2, and 3 paired together with an int of 4. So I can do basically any data type. There's no restriction on this whatsoever. You can also do n tuples, meaning that you can pair just about any number of values together and return these. And you also have options, records, lists, arrays, sequences, etc. So basically abstract data types, most of what you could possibly imagine are defined in the F# library already. Okay, another abstraction mechanism is this thing called the type augmentation, and I have 2 examples for that. Here we defined a trig data type, which is basically a representation that I intend to use for trigonometric functions or expressions that can contain a number or sign or cosine, and I also have some algebraic operators like addition and multiplication, and I have an inverse, which is 1 over x. But then I can say, okay, let's enrich this complex type and add additional members which are not actually represented as a separate shape, but they are actually broken down into a series of the existing shapes. For example, I have a static member here for tangent, which is simply just sine of its parameter multiplied by 1 over cosine, in other words, sine over cosine. Same way I can define a cotangent, or if you want, I can define an operator which can add these values of type trig, or actually not add, but divide. So I have those tan, cotangent, and the division operator defined all in terms of the basic ones, basic shapes. So in fact, from outside, this type appears to have 9 different shapes, but actually everything is broken down into 6 basic shapes. So this is what we say that less is more. We have a more enriched data type, but actually represented with fewer constructors. So that's an example for enriching a complex type. What about augmenting types? For example, I have here in the system module, I have the int32 type. This is a basic .NET int32. I can extend this, I can augment this type and say, all right, I want to tag onto it a new thing, a new function called isPrime. And the way I do that is very easy. But first of all, I've wrapped the whole thing into a module, so I don't get confused. I call the module number theory extensions. I put a function there, isPrime, which basically, using some naive algorithm, checks whether a number that is given to it is a prime number. And then basically I augment the int type with this new member and just call the isPrime function. But remember, the whole thing is basically wrapped into this module. So what I have to do is I have to open this module before I can start trying to find prime numbers. So what I do is I open the number theory extensions module and I pick a number like number 3 or 6 million, whatever, and I just basically say isPrime, and I get true or false. So imagine how powerful it is. We'll eventually get to the end of this presentation, hopefully soon. How much time do I have? I lost track. Does anybody know? No? Okay, I'll just go on then. Eventually, at the end of the presentation, we'll look at some link stuff. And link is one of these newer technologies that rely on augmentations. They actually call these extension methods in C# and VB. As you can see in F#, we don't need that because we have an augmentation mechanism, which is much more powerful actually. This is why it's called something else. This is why it's called augmentation. Okay, now it's time to really get into some dirty stuff. There's something called the computation expressions or workflows. These can assume different forms. You have sequence expressions, you have asynchronous workflows, you have probabilistic workflows. You can define your own custom workflows if you want. And you can have quoted workflows. So here I say, okay, give me a sequence between 0 and 2. Naturally, these are integer sequences. So I get back 0, 1, and 2. Okay, give me a float sequence between -100 and 100, and you get the same thing with 1 increment, but using doubles. So I actually have a double sequence there. I can do the same thing with big ints. Okay, give me a sequence from 1 to, I don't know, 100 million. It's probably more than that, but you get the point. So you can imagine that this is not allocated on the fly. If I did this sequence my computer wouldn't crash, although it would probably consume more memory than I have. So what was the secret? Well, the secret is that these sequences are actually not only just a general term to refer to any collection or enumerable objects, but they are also lazy. And that's a key distinction here. We talked about laziness versus eagerness. Sequences here are lazy. That means if you ask for its first element, then it evaluates the first element, but nothing else. So I can just as well recursively define a sequence which is infinite and just keep asking for values from it, but it will never crash or never go into an infinite loop because it's lazy. You can also have skip values. These are something, okay, don't use the increment 1, use something else. So here I'm saying, give me a sequence between 0 and 5, but with increments of 2. So I get 0, 2, and 4. 6 would fall outside of 5, so you don't get that element. Okay, we also have pretty easy ways to iterate through these sequences. It's a for loop, actually. You all have seen this in C#, so it's no big deal. We have aggregation, and this is where the fun stuff comes in. This operator we defined earlier, remember? This means that we push the parameter dir onto the directory get files. But it's a different way of putting it, and actually it makes more sense. This is a function that if I give a directory to it, it will find all the files in the directory plus all the files in the subdirectories. And the way it does that is it appends two sequences. First, it will ask all the files in the current directory, then ask all the directories of the current directory, and basically find all the files of those directories and concatenate them. So as you see, we are starting to compose these functions, and suddenly in just 2 lines, we express something pretty complicated. I mean, I challenge somebody to write this in C#, and if you can do it in 4 lines, I will pay your dinner. So here's an example. You basically find all the files in your projects directory, and you list, and here you get a sequence, a lazy sequence that you can iterate through. I also have comprehensions. These are basically ways to generate sequences based on a pattern. Here I'm generating a tuple pattern. For every number between 1 and 100, I should get a sequence of tuples where the first part is the number itself and the second one is its square. And it's just a one-liner again. And using these sequence comprehensions, I can express the all files function that we just covered here in the previous slide much more easily. I can say for any file in the directory that you gave me, give me back the file. And if I exhausted that sequence, then let's look at all the subdirectories and find all the files within those subdirectories and note the difference between this arrow and that arrow. The second arrow means that we will get back another sequence, so we have a sequence of sequences. So that arrow basically concatenates them all to make one nice uniform sequence for us. You can also construct arrays and lists instead of sequences by wrapping them into the list or the array operators. So here this will be a number or actually a sequence that we just like squares above, but it will not be a sequence, but it will be a list and an array respectively. Here's another way. We have a file, we want to read from it. How much more time? Can I get 5 minutes? Okay. So here we defined a reader, a file reader, and note that we have another keyword called use. Use is a very convenient way of releasing resources. It's the same as a let, but after the scope, after we run out of that scope, it will automatically be reclaimed. So here we basically just return each line, and I can read from it. So I have this reader that reads from a file called t.txt, and I say, okay, from the reader, let's take 3 different lines, and those are the ones I have. Here's a random walk, is a recursive sequence. Basically, you give a parameter to it, and from that it starts to go left or right randomly and just generate you infinite sequences for a random walk, all in 2 lines. Fetching web pages asynchronously. We have a list of museums and their web pages. And here's an asynchronous method that basically fetches all of these. It goes to the website, fetches the content, and prints out how many bytes it did. But it does this asynchronously. If you notice here, we have an async. This is actually the asynchronous. So before we used sequence, for example, that was a computation expression for a sequence. This is an asynchronous computation expression, which means it has this funny keyword here with an exclamation point. That means, okay, bind the value of get respond async, but actually do it asynchronously, so don't wait for the result. And if you have more than these, like I have a number of museums, I basically spawn for each of them this function that I just showed you, and it will just do it. And as you can see in this trace, what it does, it starts to create a request for each of those museums and get the responses, but at different times. So it's all random here. This is what you would say or call a non-deterministic computation. It's asynchronous. Okay. Same thing with file processing. Let's say I want to process a number of files and transform them as images. It's all 6 lines. And this is how I invoke it. I have a variable that defines how many images I have, and I start to process them all asynchronously and run them using this async module. We also have probabilistic workflows that can do probabilistic events and model them. Very, very expert level stuff. How do they work? I don't have the time to explain. Basically, they have computation builders and some syntax desugaring. If you're interested, I can talk about that after the talk. I don't want to cover imperative or object-oriented programming. It's crazy, just running through. And language-oriented programming, we have active patterns, reflection, quotations, and the link stuff. Let me just cover the link stuff. So we have 3 different mechanisms to access link. We have link for in-memory objects. And actually, we don't need the link libraries for that because the power of functional programming is already there. I can use aggregate operators on in-memory collections, and poof, I have everything. So here, I renamed the select and where operators. And basically, here I have a list of data, people, and I'm selecting those whose name starts with an R, a letter R. So that's that easy. It doesn't have any link relationship. It's just basically higher order functions. The XML stuff, it's basically functional construction of XML objects or documents. We don't care about that. And the link to SQL is a bit more involved. Here we need another mechanism called the F# quotations. There's this SQL quotation, which takes a quotation and returns the value representing the type of that quotation. And here's an example. This query inside the quotation operators is actually an F# query, but it will get translated to a SQL code and executed against the database. So this is just basically, it looks very similar to a SQL code, but it's actually typed, just like with a link in C# or VB. And out of that sequence or results set, we take 5, and then we print those. I showed you the command line environment, the interactive. This is what it looks like, and the visual plugin looks like that. If you have questions, you can come to me and talk to me after the lecture. And any questions? If not, I would like to just mention that we do have a book on this. It's called Expert F#. It's been published a few months ago. And there's luckily a tremendous interest in it. So if you are interested, come and talk to me. Thank you very much for your attention, and I wish you good luck.